Very important section here, 2.7. We're talking about derivatives, which are going to be one of the central concepts that we talk about, and really what Chapter 2 has been building up for. All these sections that we've done so far in Chapter 2 have been building up and pointing towards this concept of a derivative. Now remember, we define the slope of the tangent curve to be the limit as h approaches 0 of f of x, or f of a plus h rather, f of a plus h minus f of a divided by h, and we said that was the slope of the tangent curve, or the tangent line, I should say, slope of the tangent line to the curve y equals f of x. And so we've talked a lot about this in Chapter 2. If we have some graph, some curve here, and we pick some point on our curve, say, let's say right here is A, and then we draw a line tangent to the curve at that point A comma f of A, the slope is that limit. That's that limit as h approaches 0 of f of a plus h minus f of a divided by h. And what this tells us then, again, since how the slope of the tangent line is also really measures the change in the function. And so this slope here is the rate of change. It's how fast the function is changing of the function f at the point A. And when we talk about the rate of change of something, we're going to use a word for that, and the word is going to be the derivative. So we're going to say this is the derivative. This slope here, this is talking about the slope of the line tangent. It's the derivative of f at the point A. And the notation that we're going to use then is the function f with a little apostrophe there, and we read that as f prime of a. F prime of a is the derivative of the function f at the point A. And again, all that means is how fast the function is changing, and we measure how fast the function is changing by looking at the slope of the line tangent. We find the slope of the line tangent by taking that limit as h approaches 0 of f of a plus h minus f of a divided by h. Now we can also define f prime of a to be the other definition, the limit as x approaches a of f of x minus f of a divided by x minus a. And of course this definition is analogous to the previous definition with h. We can go from this definition to this definition by just letting h equal x minus a. So those two definitions really say the exact same thing, just a kind of different way of writing it. So, but again, the notation that we want to get used to writing here is this prime notation, f prime of a, and we read that as the derivative of f at the point A. And so the thing to remember is always that f prime of a represents the slope. So again, if we look at some function here, and let's say we have a point A right here, and we want to find, let's say, the equation of the line tangent to the curve at this point. Well, this point right here is a comma f of a, the value of the function at a. And we want to find the equation of this line tangent. Well, we know that the slope is one of the things we need to know the equation of the line. And the slope is now going to be represented as f prime of a. So using the point slope form, we can say that y minus the y value of the point on our line, f of a, is equal to our slope, m, or f prime of a, times the quantity of x minus the x value of the point on our line, which is a. So we can always find the equation of a line tangent to a curve, y equals f of x at the point a comma f of a, by using this formula right here. Y minus f of a is equal to the derivative f prime of a, which, remember, the derivative is the slope of the line tangent, times the quantity of x minus a. We'll look at some examples of that as we move along here. Alright, and so then we can also think of the derivative as the rate of change, the instantaneous rate of change. Remember, we did some definitions where we said, let's let delta x equal the difference between two x values, x2 and x1. And then we will let delta y, delta meaning change in, be the difference in the y values of the function at those corresponding x values. So that'll be the function at x2 minus the function at x1. So let's draw a picture here again of what we're looking at. And here's our curve here. And let's say here's x1, and let's say here is x2 for starters. And so what we're going to be looking at then is this slope of this secant line here from the point x1 comma f of x1 to the point x2 comma f of x2. And what is that slope going to be equal to? Well, that slope of this secant line is going to be the change in y divided by the change in x. If you think about This line here, we can think of it as the hypotenuse of a triangle. This distance of the horizontal here is delta x. This is delta y. And so how do you measure the slope? Well, it's the change in y over the change in x. And so what's going to happen then is x2 heads towards x1. This point here moves along the curve, and these secant lines get closer and closer to having the slope of the actual tangent line, which may look something like that. And so we can say then that the instantaneous, and this, remember, this measures how fast a function is changing. It's a rate of change. The change in y divided by the change in x. The change in the output divided by the change in the input. So we could say then that the instantaneous rate of change, as defined by what we've just done here, is going to be equal to the limit as delta x approaches 0. The change in x approaches 0 as this x2 approaches x1. The change in x, delta x, approaches 0 of the change in y over the change in x. And that's just a measure of the slope of the secant line. And so we could also say then that's the limit as x2 approaches x1 of the change in y, which is f of x2 minus f of x1, divided by the change in x, which is x2 minus x1. And so the derivative then, as they state there in the bottom of page 150, is going to be the instantaneous rate of change of y equals f of x with respect to x when x is equal to a. So we can think of that derivative as telling us exactly how fast a function is changing at that particular moment in time. And again, if you think of a function, if talked about this a little bit in previous sections, if s equals f of t is your position function, well, then if you take b of a and let that be f prime of a, then your velocity is given by that instantaneous rate of change. That's your velocity. It's the derivative, and this is going to be the velocity at t equals a, or the instantaneous rate of change at t equals a. And remember that the derivative f prime of a, which is what the velocity is equal to, can be thought of as the limit as delta x approaches 0 of delta y over delta x. And so the units on your derivative, if there's units given in the problem, the units are going to be always the units of the output of your function, the units of y, divided by the units of the input of your function, which in this case is x, although I probably should be using t here because we had an independent. Let's say t and t here. What we should say is, let's write it this way. We'll say that the unit of the derivative are always going to be the units of the dependent variable, which is usually going to be called y, but not always, divided by the units of the independent variable. So when we want to put units on our derivative, this is what we put on: the units of the dependent variable divided by the units of the independent variable. In other words, like we said, if we have s equals f of t as a position, so the position in meters after t seconds, well then f prime of a will be given in meters per second. The unit of the output, which is meters, divided by the unit of the input, which is. Okay, that's it for this video. We will look at some examples in the next video.